So now let's discuss the non-homogeneous linear differential equations, how to solve them. Okay, non-linear. Basically, we are discussing ordinary differential equations. Okay. So just to begin this, we will approach in the same way. We'll first see what happens for a second order differential equation non-homogeneous case, and then we'll extend the same thing to our higher order non-homogeneous. So consider non-homogeneous second order D. Okay, so this looks something like this. I can write second order non-homogeneous case something like this. F of x. So this makes the differential equation non-homogeneous. Now we are and now the corresponding, remember, the corresponding homogeneous equation for this differential equation will be just keeping the right hand side 0. So a2 x d square y by dx square plus a1 x dy by dx plus a0 x y is equal to 0. So this is the corresponding homogeneous equations. Now with constant coefficients we have seen how to find out the independent solution. So assuming that two independent solutions exist, two independent solutions exist, y1x and y2x. So this is 1 and the 2 is corresponding homogeneous equation for 1. So this for the homogeneous equation 2. So assume that you have found out the two independent solution for a homogeneous equation 2. Okay, are known. Okay, and so the general equation will be something like this: c1 y1x plus c2 y2x will be the general solution of 2. This is by theorem 1, which we have seen. Okay, now what does theorem 2 says? Theorem 2 suggests the general solution of the non-homogeneous case, non-homogeneous DE, which is represented by equation 1 here. So what does theorem 2 says is that the theorem 2, or basically the fact 2, which we have just seen at the beginning of linear differential equation case. Okay, what it says is the general solution is basically this is denoted as complementary function. So complementary function plus Butler integral. So this is basically for the one of the solution for the non-homogeneous case. And what it says is you have to combine the corresponding corresponding general solution for the homogeneous case. You have to combine with this y p of x in order to get the general solution for the non-homogeneous case. Okay, so this, let me write in this case, this I can write as c1 y1x plus c2 y2x. Okay, solution, and this is, so this is called the complementary function or the complementary solution. Okay, which is nothing but the general solution of the homogeneous case, general solution of the homogeneous, the corresponding homogeneous equation, the corresponding homogeneous equation. And this is the particular integral or the particular solution. This is called as the particular solution. So now extending this to general equation, we still have the same thing, the complementary function and the Butler solution. So complementary function we have already seen the ways to find out complementary function, because we have already seen how to solve homogeneous linear solution, how to find out particular solution. So let's see the methods to find particular solution. Okay, so remember, particular solution will be there only when you have the homogeneous case. When you have the non-homogeneous term, f of x not equal to 0. So here you have by two methods. One is by inverse operator method, and the second is by method of variation of parameters. Method of variation of parameters. So we'll discuss each step by step, not going into the detail thing, because detail will require a lot of derivations. So we'll just express the rules for each of these methods, how to solve them, and finding out the particular operator. So let's see the method of inverse operator. What does inverse operator means, and then we will see how to use this method in order to solve the particular solution, how to find out the particular solution. So what does inverse operator says? Okay, so the let's first go to the definition. So the definition of this is that 1 by f of d x is that function of x is that function, let me write down the definition first and then we'll explain, not containing arbitrary constants so which when operated by f of d upon by f of d gives x. So what it simply means is that it means that if I operate f of d to this 1 by f of d x to get x, then this 1 by f of d x basically satisfies the equation f of d y is equal to x, and therefore this is called the particular solution. So what it means is, most of the time you can write a linear differential equation in this form: f of d y is equal to x. So now y is something of this form because we have seen at the top in the definition that it satisfies this differential equation. So in a sense it is called particular integral. Okay, so now what happens is, generally the differential equation of higher order, generally the differential equation, I am writing differential in a short form, of higher order first degree is written in this form: f of d y is equal to x, and therefore y by 1 by f of d x becomes your particular integral. Okay, now let's see some properties. This was the definition. Let's see some properties of this particular integral. Okay, what it says is that 1 by d, if I operate on x, it will become x dx. So remember, what is capital X here? Now we are discussing capital X is some function of small x. Okay, basically the right hand side terms which we were calling f of x, and now we are calling it as capital X. Okay, so this, okay, so this is the general thing. So this is the one of the property: 1 by d x is integral h dx. So how do you derive this? So this is 1 by d x, let this be y. Now if I operate d, operating by d, so operating by d is nothing but d by dx. So if I operate by d, what will I get? D 1 by d of x is equal to dy. So this will be basically x, and this will be dy by dx. Okay, dy by dx. Now if I integrate, so now if I integrate both sides with respect to x, okay, now if I integrate both sides, I can write x dx as y, integral h dx as y, and that I can substitute it back here, so I'll get 1 by dx as integral h dx. So this is what we proved. Okay, similarly, we have another property of the differential operator. 1 by d minus a into some function of x will become basically e power ax integral x e power minus ax dx. Well, how do we prove this? So similarly, let 1 by d minus a capital H to be y, and now operate by d minus a on both sides. So when you operate by d minus a on both sides, so I'll be getting d minus a 1 by d minus a into x is equal to d minus a into y. So this is nothing but x, and uh, this is dy minus ay, which is dy by dx minus ay, and this is capital X, which is someone else. So this I can just rearrange, and this becomes basically a linear t of first order. And remember that how did we solve this? By the integration factor method. So integration factor method was integral it was e integral p of x dx, which was e minus a dx is e power minus ax. This, and the solution is y integrating factor into integration e q, basically q, and then the integrating factor dx plus some constants. Now integral q is here capital X, integrating factor is e power minus x dx plus c. Okay, and integrating factor here is y e power minus x. Okay, so I can write this as y e power minus ax. Okay, okay, so this constant I can multiply throughout. Now here no constant will be added, or you can just choose a constant to be 0. So I can write this in this case, because this equation uh, d minus a, then 1 by d minus a x is equal to y, that doesn't have any constant. So I can just ideally choose to have no constant, because going by the definition of the inverse operator. So this I can write y ax integral x e power minus ax dx. So this is what we got. And remember, from where we started 1 by d minus ax equal to y. So this is equal to y, and this is equal to e power ax x e power minus ax dx. So this is one important property of the inverse operator. So we have seen 1 by dx, and we have seen 1 by d minus a into capital X. Okay, so these we'll probably use in order to find out particular integrals. Now, based on a lot of derivations, we have come out with some common rules for finding integration. So let's see rules for finding particular solution or particular integral. Okay, so we have come out with a lot of rules. So let's now consider a general equation which is of this form. So here we are concerned only with the constant terms, because constant coefficient case is only there in the syllabus. And now this f of x we are calling as capital X, which is nothing but just a function of x. So in symbolic form, I can write this as d power n plus k1 d power n minus 1 plus k2 d power n minus 2 so on kn y is equal to capital X. So the particular integral pi will be basically the inverse operator. So this you can actually ideally call this term to be f of d. So f of dy is equal to X. So this is 1 by f of d into capital X, or just writing it out completely, into capital X. Okay, this is what is your particular integral. Okay, so let's see how to find out this particular integral. Okay, what are the different rules for finding particular integral? So considering the form to be f of d y is equal to x, now see the rules, okay, for finding particular integral. So first case, when capital X is exponential form or e power ax, which is some constant, then I can write 1 by f of d into e power ax. So now by the derivation, what it means is, if you have something like this, you can always write e power ax by f of a. So this will be your particular integral or particular solution. Now what if f of a is 0? If f of a is 0, then 1 by f of t e power ax will be basically x into f dash a into e power ax. So if you have the directly f of a, when you substitute and if it comes out to be 0, then what you have to do is you have to just take the derivative part of f of x. And now if f dash a also is 0, then the particular integral, this is the particular integral when f of a is 0, the particular integral will be x square 1 by f double dash a e power ax. So this will be the particular integral that time, and so on. Okay, if so, this is rule 1. Okay, so now let's see the rule number 2, which is if x is capital X is of the form of sine ax plus b or cos ax plus b. So in that sense, then what it says is, if you have something like this, I mean, try to put f of d, try to bring in terms of d square, and if you are succeeded in order to bring in terms of d square, then this particular integral term will become basically, in the place of d square you have to substitute minus a square. That is what it says. So what it says is, put d square is equal to minus a square when you have something like this square. So basically f of d you have to try to get in terms of f of d square. I mean, that will happen only when you have d, all the d terms should be in the form of d square. Now if, and this will be basically f dash minus a square sine ax plus b, the case when f of minus a square is equal to 0. Okay, and so on. I mean, this will be h square f double dash minus a square sine ax plus b if your f dash minus a square term is 0. Okay, and similarly it is for cos ax plus b also. We have written here all the sine terms, but the similar thing exists for cos ax plus b as well. Okay, so that's what you have to do. You have to always try to express if it is in d square. If it is not in d square, then you have to basically use some other techniques. Okay, now rule number 3, when capital X is a function of it's of the form x power m, so then your particular integral will be 1 by f of t x power m, and this you can write fd inverse x power m. So what you have to do is you have to expand fd inverse in ascending power of t as far as the terms d power m. So this will be clear when we solve problem. Okay. Okay, so these are basically the general three rules. I mean the three rules for finding the particular integral. Whereas the general rule is like this. If you don't know, I mean the form of capital X, if it is not expressible in the form of e power x or sin ax plus b or x power m, then the general rule is f of t, just try to express in this form in terms of partial fractions, something like this. And once you express in this, where m1 m2 m are the roots of f of t. Okay, so when you put f of d is equal to 0, okay, get the roots m1 m2 so on till m power n, and then put in this partial fraction format. So once you know this, okay, so now your f of t x will become a1 d minus m1 x plus a2 d minus m2 x plus a3 d minus m3 capital X plus so on. Okay, and now your particular integral, which is nothing but 1 by f of d. So this is basically each of this term is basically something. Now we have to use the property 3 which we have derived. Okay, we have derived after some time back that d minus a, okay, of capital X is basically e power ax integral x e power minus ax d. So in the same way, each of these terms is basically a1 e power m1x integral e power minus m1x capital X dx plus, similarly the second term will be a2 e power m2x integral e power minus m2x integral x dx, similarly so on for all the terms. So this is one general method. Okay, if the form of capital X is not whatever we have discussed in 1 2 3, then this partial fraction method you can just use to find out the particular integral. Okay, so now let's see the working procedure for a non-homogeneous case, and then we'll solve some problems in order to finding out the particular integral. Okay. Okay, or let's at this point actually take some example problems in order to finding out the particular integral. So let's see some example problems of finding particular integrals, and then we'll find out we'll see some. So first few examples will be to finding out the particular integral, and then we'll see examples for the complete non-linear complete non-homogeneous linear ordinary differential equation. We'll see how to find out the complete solution, that is complementary function, as well as the particular solution. So now particular solution is sometimes called as particular integral, so don't get confused. Now find the particular integral of d square plus 5d plus 6 y is equal to e power x. So this I can write y f of d is e power x, and this is something like this. This is the particular integral is this. Okay, so how do I find out? I mean, this is my particular integral. So how do I find out? Now, comparing with the rules, what it said was, yeah, so what it said was, just substitute e power x. So a is 1, and f of a is what? F of a is 1 square plus 5 into 1 plus 6. So this is 6 plus 6 is 12. So that's what it said. E power ax f of t is, the particular integral is e power a f of a, and going by that it is e power x by 12. So the particular integral for this is e power x by 12. Okay, so it is so simple. Now let's take another example. Okay, so let's take another example. Find pi of d plus 2 d minus 1 whole square y equal to e power minus 2h plus 2 sine hh. So sine hyperbolic function. So before this, before starting the problem, we know that sine hyperbolic function is expressed in this form: e power x minus, sorry, by 2. Okay, that is the general definition of hyperbolic. Don't worry, I mean, it will be given. I mean, the hyperbolic functions, most of the time in GATE, the definitions will be given. It's a exam of, it's a test of your concepts rather than test of memory. Okay, but for this problem, let's recall sine hyperbolic to be e power x minus e power minus x by 2. So I can write the given equation to be d power minus 2 as e power minus x plus e power x minus e power minus x. So I can write just going back to the question, this was e power minus 2x, so e power minus 2x. Okay, so this is basically e power minus 2x plus e power x minus e power minus x. So this is what is the general. So now the particular integral will be 1 by f of t, which is this, and your capital X is all this. Okay, so now we can apply simultaneously, or we can apply step by step. So let's apply step by step. Okay, let's apply step by step individually, I mean on each of the terms individually. So in that case, let's consider this case separately. Okay, this I can write as d plus 2 into 1 by d minus 1 whole square e power minus 2x. So now I can apply that f of a by 1 by, I mean, sorry, I can apply this formula f of d, which will become e power x by f of a, provided that f of a is not 0. So I can apply that to be, so e power minus 2x by minus 2 minus 1 whole square. Okay, so that will be basically 3 square, which is 9. Now e power minus 2x by d plus 2. Okay, now we know that now if I substitute, apply the same formula, my f of a will be 0. So then what I have to do is I have to just use the second formula, that if f of a is 0, then 1 by f of d e power x will be x e power x by f dash of a. So let's differentiate. F dash of d will be 1, so 1 by 9 into x e power minus 2x. Okay, so that is the for first term. Now second term is d plus 2 d minus 1 whole square e power x. So this, how do we get this? Well, how do you get this? Well, here I can just apply d minus 1. Later, first I can apply d plus 2. Okay, it doesn't change. So this will be d minus 1, and e power x will be basically e power x, e power f of e power x by f of a. So substituting 1 here, so 1 plus 2, it is 3. So 3 by 1 minus d minus 1 whole square into e power x. So this basically d minus 1 whole square I can expand, it comes out to be d square minus 2d plus 1, d plus 1. So f dash d, now if I substitute f of a directly, it will become 0. So just finding out f dash d, which is 2d minus 2. Now here also if I substitute f of 1, f dash 1, this will be 0. So completely finding f double dash d, which is 2. So this will basically become x square e power x by f double dash a. Okay, this is the general form. So it will become 1 by 3 f double dash d is 2 into x square e power x. So it will be x square by 3 to 6 e power x is the second term. Wonderful. So you have to pay attention to whatever the rules we have derived. And similarly, the power minus x term. So this, if we can substitute directly, it will not become 0. So t plus 2, it will be e power minus x by minus 1 whole square. So this will be 1 by d plus 2 e power minus x by 2 square, which is 4. And then again you can substitute back minus 1 there. So minus 1 plus 2 into 4 into e power minus x. So this will be 1 by 4 e power minus x over e power minus x. So the combining all this thing, the particular integral for the given function, the given differential equation, the particular integral is combining all these terms, this and this, will get 1 by 9 x e power minus 2x plus x square by 6 e power x plus 1 by 4 e power minus x. Okay, so x by 9 e power minus 2x, x square by 6 e power x, 1 by 4 e power minus. So this was the particular integral for this function. So another problem, in order to find out the particular integral, okay, let's take another example where it is given d cube y by d x cube plus 4 dy by dx is equal to sine 2x. Find out the particular integral of this. Okay, so let's express in that form, in the symbolic form. This comes out to be something like this. Okay, and the particular integral is basically sine 2x 1 by f of d, and this is your f of d. Okay, so this will be 1 by d cube plus 4d d cube plus 4d, okay, sine 2x. Okay, so now I can just I mean I have to express this in the form of d square. So I can actually write in this form d square plus 4, and then apply first d square plus 4. So so this is in the form of, so I can put d square as minus a square, which is minus 2 square, which is minus 4. If I put there, so this will be minus 4 plus 0, this is getting to be 0. So then I can have to write x sine 2x by f dash d square. Okay, f dash d square. So how do you take f dash d square? Okay, so let's take now, so this is not valid. So now f of d is your d cube plus 4d. Let's take f dash d, it will be 3d square plus 4. Okay, and now if you substitute minus 4 here, it will be 3 minus 4 plus 4, this is not 0. So therefore the solution will be solution of 1 by d cube plus 4d into sine 2x. The solution will be x into 1 by f dash minus a square into sine 2x. So this comes out to be x into 3 d square plus 4. So 3 minus 4 plus 4 into sine 2x. So this comes out to be x sine 2x by 8 minus 8. Okay, so this is the particular integral for this. So we have seen for the exponential and sine terms, and you can solve many other problems in order to get the particular integral for various forms. So let me now write down a working procedure to solve the non-homogeneous higher order differential equation. Okay, so this is the general thing which we are looking. So if you are able to express something in this form, so remember we are worried only about the constant coefficients. Okay, we capitalize this function. Then step 1 is always to find out the complementary function. of the corresponding homogeneous equation, putting capital H to be 0, taking only the right hand part, find out the complementary function. For this you have to write the auxiliary equation, get the roots, and then depending on whether roots are equal, complex or unequal, we have already laid down various cases in which the complementary solution falls. The second is to find the particular integral, which we have just seen. What are the ways to find out particular integral? But there is another way, another method. Till now we have seen only the inverse differential operator method. We have laid out rules for capital X. If capital X is e power ax or sin ax plus b, or cos ax plus b, or x power m, or the general partial fraction method. So all that we have laid down rules. So this is the general step. So once you have to find a complementary function, and then the particular integral, and therefore then the complete solution is basically the complementary function plus the particular integral. This is your complete solution. Okay, so let's now solve one complete problem which describes how to find out complementary function and how to find out particular integral, and then we will be done with the differential equations, uh, the higher order differential equation.